Have you ever found yourself asking that classic question, what if? What if we actually raised our prices? Or what if we changed this one company policy? Well, it turns out that answering those what-if questions is one of the single biggest challenges for modern AI. It's because it's not just about what did happen, but predicting what would happen. This is the world of counterfactual prediction, and we're about to dive deep.
So here's the thing. The core problem is that our data can sometimes be an incredibly convincing but totally misleading witness. It can show us all these patterns that seem to point in one direction, but the reality is completely the opposite. So the big question we're tackling in this explainer is, why does our data lie to us, and how on earth can we teach a machine to see the truth behind the lies?
All right, let's start with a fantastic puzzle, pulled straight from the research. Imagine an airline. They're looking at their sales data, and they spot a really weird pattern. Whenever their ticket prices go up, they actually sell more tickets. Now that just makes no sense, right? I mean, basic economics tells us the exact opposite should be happening. So what is going on here?
And that brings us to our first section, the prediction puzzle. We're about to see exactly why a standard off-the-shelf prediction model gets this completely and utterly wrong.
The whole problem really breaks down into two competing stories. On one hand, you've got the naive view, the one the raw data screaming at you, higher prices lead to higher sales. Simple. But the reality is much sneakier. There's a hidden culprit at work. An unseen event, let's say a huge conference in town, is causing a spike in demand, and it's also causing the airline to raise its prices to match that demand. You see, the price isn't causing the sales. The conference is causing both. Now, this hidden culprit problem actually has a technical name. It's called selection on unobservables, and it is the absolute core challenge of causal inference. It just means that some hidden factor that you can't even see or measure is secretly pulling the strings in the background, making it look like one thing causes another when it really doesn't.
This brings us right to the hidden variable problem. Now we can really start to name the players in our little mystery.
So in any causal mystery like this one, you've basically got three key players. You've got the treatment, which is the policy you're actually changing, in our case, the airline ticket price. You've got the outcome, which is the result you're measuring, so ticket sales. And then you have the hidden confounder, our culprit, that unobserved conference that's messing up all our data.
And this is what makes it so dangerous. The researchers put it perfectly. They said a standard machine learning model would look at this data and confidently tell the airline, hey, raise your prices to sell more tickets. But we all know, just intuitively, that the real relationship is negative. That advice is a recipe for a truly disastrous business decision.
Okay, so how do we solve this? How do we find the truth that's buried in all this misleading data? Well, we need to find a clean signal. We need a clue that hasn't been tainted by our hidden culprit.
And this untainted clue has a name. It's called an instrumental variable, or IV for short. And you should really think of the IV as the hero of our story. It's this special kind of data point that has a superpower. It can affect our policy, but it is completely immune to the influence of that hidden confounder. It's clean.
And to make this really concrete, let's go back to the airline example. The cost of fuel is a perfect instrumental variable here. Why? Well, think about it. When fuel costs go up, the airline has to raise ticket prices. So it definitely influences the policy. But, and this is the crucial part, the global price of oil has absolutely nothing to do with whether a specific city is hosting a conference this weekend. It's a clean, independent reason for prices to change.
Now, for an instrumental variable to work its magic, it has to follow three very strict rules. First, relevance. It's got to actually affect your policy. Check. Second, exclusion. It can't have its own secret direct path to the outcome. And third, unconfoundedness. It has to be completely independent of the hidden culprit. Our fuel cost example, it nails all three.
So, we've found our untainted clue. That's a huge step. But now we need an advanced forensic tool to actually use it. And that tool is the Deep IV framework. At a high level, Deep IV is this really clever architecture that uses not one, but two deep neural networks that work together as a team. And their combined mission is to use that instrumental variable to surgically isolate the true underlying causal relationship. So here's how this two-step process actually works. Think of it like a two-detective system. The first detective, that's the first neural network, it has one job and one job only, to figure out how our clean clue, the fuel costs, affects the ticket price. It just learns that relationship and ignores everything else.
Then, the second detective takes only the price changes that the first detective certified as clean, the ones caused by fuel costs, and it uses only that clean data to predict the real effect on sales. It has effectively learned to completely ignore all the messy, misleading price changes that were caused by the conference.
This all sounds great in theory, but does this advanced forensic tool actually work in practice? Well, the researchers put it to the test, and the results are in.
Okay, so in these simulations, the researchers know the true answers, so the goal is to get the lowest possible error. You can see here a naive model is way off. Traditional methods like something called 2SLS, they do a bit better. But look at Deep IV. It gets dramatically closer to the ground truth with the lowest error by a really wide margin.
And this wasn't just on some simple, clean problem. The researchers ran a wild test where different types of customers were represented by entire images of handwritten digits. So the model had to figure out what kind of customer it was looking at just from the raw pixels of their handwriting. And even in this incredibly complex, messy environment, Deep AV's causal approach just blew the naive prediction models out of the water.
But you know, the most compelling proof always comes from the real world. When they looked at real search ad data, a naive model predicted a totally absurd 70% drop in clicks when an ad just moved from the first to the second position. Deep IV, on the other hand, it calculated a much more realistic and frankly actionable 12% drop. And that right there is the difference between a nonsensical metric and a true business insight. And that's the crucial point. This isn't just some academic exercise. Solving this kind of mystery leads to much smarter, real-world decisions for pretty much everyone.
I mean, the applications here are huge. This kind of technology can help us optimize pricing, evaluate economic policies, understand the real effect of a medical treatment just from historical data, and basically, it helps us make better decisions in any situation where a simple A/B test is either too expensive or unethical or just flat-out impossible to run.
So if there is one thing you take away from all of this, let it be this. Deep IV gives us a flexible and powerful new tool to stop being fooled by our data. It helps us finally move beyond just predicting correlations and start truly understanding cause and effect. And that leaves us with one last really important question to think about. In our own businesses, in our policies, maybe even in our own lives, what critical decisions are we making right now based on data that might just be lying to us?